All right, this is your recording for lesson 39-4. We're going to be talking about plotting residuals. So remember from the previous lesson that a residual is the difference between a predicted y value and the actual y value. So when we're using a line of best fit, the residual is positive if the value is above the line and it's negative if it's below. So when we were looking in the last lesson at the marathon data, it's obvious that the relationship between the finish time and the age wasn't linear. However, there are times where data appears to be linear, but actually isn't. So maybe we're only looking at a small section of it, whereas, the curved trend maybe is on the ends. So it's important that we have ways to kind of fish those situations out, because we might run a linear regression and get an R correlation value that shows a strong relationship. And that doesn't mean that that isn't a strong relationship for that part of the data. But again, if we look outside of it, sometimes it shows a different trend. So another way to decide whether a curve is better than a line is to look at what's called the residual plot. So sometimes we can see it just in a scatter plot. Sometimes the scatter plot shape itself looks like a curve, but sometimes it looks like a line and then it actually isn't. So what we can do as another tool to help us is look at what's called a residual plot. And what we do is we plot the actual value, the x, and then its residual value as an ordered pair. So if we go back to the bear data that we had used at the beginning of activity 39, where we were talking about predicting the bear's age based upon its weight, and here were our predicted values from our line of best fit. Here were the actual values for the age of the bear, so we had our residuals that we calculated. So when we're plotting a residual pair, as I said up here, the first value is the x value. So not what we're predicting, but what we actually know, which is the weight. So weight is x here, and then the residual. So here they're showing you that it would be 88.2.05 for bear 1's ordered pair for the residual plot. Remember that if you look at your embedded assessment on that last page, one of the things that they give you is a residual plot in order to help you make decisions. So really important that you understand how to interpret these. So what it wants us to do in number 1 is to complete the residual plot by adding the other 8 points. So for bear 2, we would plot 88.2 for the weight and 1.05 for the residual. So same x value, but now 1.05, which would be just barely above 1. So about right here. I should probably use a different color other than black, but I have it on red and it doesn't appear. There we go. So there, now we have it in red. Okay, so what I'd like for you to do is to take a minute with your group and go ahead and plot these ordered pairs. So if you could pause the recording for just a couple minutes and then come back once you're done. All right, so check your data with my graph down here. One of my points, sorry, this one, I slipped a little with my pen, so that one looks rather large. But you can see where each of these values are. So we had bear 2 here, bear 3 down here, bear 4 right on this line. Bears 5 and 6 both had the same weight, so those are these 2 points. Bear 7, bear 8, and bear 9. So just double check your plots to make sure that they are correct. So when we look at the residual plot, we'll notice that there is no pattern. and the points appear to just be random. So if we were looking at this as a scatter plot instead of a residual plot, we would look at this and say, oh, there's no correlation. We can't seem to find a pattern. So what happens, and it tells you this in the math tip, is that if you have a strong pattern in the residual, that indicates that the line is not the best way to describe the relationship. So this one, because there is no strong pattern, that is actually telling us that linear relationship is a good relationship. So no strong pattern here indicates that it is indeed linear. Now they've done the residual plot for the marathon that we looked at in the last section here. Sorry, can't get it to stay still. So if we look at this residual, this does not appear to be random. There is a very strong curved pattern here, looking somewhat like a parabola, perhaps even an exponential if we ignore this as an outliner. But regardless of which type of curve we decide it is, there's definitely a strong curved pattern. And so that is telling us that the marathon data really should not be described by a line. So if we look at another example here, they've given us the shell length in millimeters for 12 lobsters as well as their age. So when we take those and we look at a scatter plot for it, which they show you on the top of page 590. So here you can see all of the data itself, the shell length, the age, and then on the next page, we see the scatter plot. So what do you think when you look at this scatter plot? If you had to describe this, what would you say about the relationship? So just go ahead and next to this scatter plot, jot down, shouldn't take much more than a few seconds, to what kind of relationship it appears that this scatter plot has. All right, so when we look at this, it would be my guess that you would look at this and say that the scatter plot looks to have a strong positive correlation because it looks very much like a line and the data is getting bigger for the age as the length is getting bigger. So it looks to have a very strong positive correlation. So because of that, we would find the equation of the best fit line, which they give to us here. So our slope is 0.0325 and our y-intercept at -1.41. It tells us that y is the age, x is the shell length. And so what we're going to do is we're going to use that equation to complete this table. It says round to the nearest hundredth, so that's 2 decimal places if needed here. So you can do this actually a couple of different ways because they give us the residual for some of the columns where predicted age is not given, which means that you could actually, instead of using the equation to predict the age, you could go back and say, well, I know that the predicted value here is 0.13, and so I know that it should be 0.13 less than the actual value. So I could do here 1.42 minus 0.13. Of course, you can use a calculator here, but that would give me 1.29. And so I can fill the chart in that way. Now, the other way to fill in the chart here is to actually use use our equation. So we know the actual age, we know the shell length, so I could use this equation and instead do negative 1.41 plus 0.0325 times my x, which is 109. So it really does not matter which direction you go here, because you should get the same answer no matter which way you do it. So if you use your calculator and plus 0.0325 times 109 and press equals, you should get 2.1325, and we're rounding to the nearest hundredth, so that would just be 2.13, which on this one, because the residual is negative, that tells you that the predicted is going to be bigger than the actual age. So we could have done 1.82 and added the 0.31, and we would get the exact same thing. So I do not care which way you do it if you have just one missing value here, because either one is perfectly acceptable. Now these next two ones, we're just missing the residual, which means that we need to just do the subtraction here. So do 2.17 minus 2.43 for this column, and then 3.7 minus 3.24 for this column. So fill those out real quick. And hopefully you get negative 0.26 for this first one, and then for the second one, negative, oops, not negative, I can't read, should be positive 0.46. Now, these last three, we do not have a choice because we don't have this column filled in or this column filled in. They're both blank, which means that we have to use our equation here in order to get our predicted age, and then subsequently to calculate our residual. So for here, we're going to do negative 1.41 plus 0.0325 times 75. And then we're going to do the exact same thing for the other two, except of course changing out that shell length x variable and replacing it with the 142, and then finally with the 148. All right, so I'd like you to take a minute, go ahead, plug these into your calculator to get the predicted age, and then take age minus the predicted age to fill in your residuals. So pause the recording again for just about 2, maybe 3 minutes to try to get those done, and then come back. All right, so go ahead and check your data with mine here to make sure it matches up. If you made a calculation error, then go ahead and fix it so that your table is accurate. So the book has gone ahead and done a residual plot for us. So all of these values, along with the shell length values, are plotted here on a residual plot. So we can study that. Notice, how much different it looks than the scatter plot, which we had too far, right up here. So the scatter plot definitely looks different than the residual plot, which was true for our bare data as well, because our bare data itself looked linear and the residual plot didn't seem to have any pattern. So number 3, describe the pattern in the residual plot. So just jot down, when you look at this plot, does it appear like there is no pattern? Does it appear that there's a strong pattern? What would you say for number 3 about the pattern that you see in that residual plot? So what I would say is that there is a curved pattern in the plot, because that plot definitely does not look like the bear plot. It has a definite curved pattern, high on the ends, low in the middle, which, remember, tells us, if there's any type of pattern there, that a linear model is probably not the best model, which is very surprising because, again, when we looked at the scatter plot itself, this looked like it had a very strong positive correlation. But that can be deceiving, and when we look at our residuals, we can see that. So number 4 says the biologists who collected these data decided to use an exponential curve to describe the relationship between age and shell length. Do we think that this is reasonable? Explain why or why not. I would say that yes, definitely. An exponential appears to be appropriate after seeing that the residual plot curves. So when they looked back at that data, once they saw the residuals, they said, well, it doesn't appear to be a parabola. I don't have any values over here. But this could, if you look, follow kind of that exponential growth shape rather than a line. So that's why we would say that this is definitely a reasonable choice for the scientists to make. All right, so now you're going to have a chance to practice some of this yourself. So our situation here is because no tortilla chip lover likes soggy chips. Well, that's true. So the chip makers are looking at frying time in comparison to moisture content. And so X is the frying time in seconds, Y is the moisture content in percent. So after 5 seconds of frying, it still has 16.3% moisture. After 60 seconds of frying, only 1.3% moisture. So I would like you to work with your group, and you're going to look at number 5 and number 6 first. So you're going to construct a scatter plot, so actually show a scatter plot of your data, and then find the equation of the best fit line. Again, the best way to do the best fit line is to use your calculator. So enter this in your L1, enter this in your L2. If you need a refresher, remember that we go after we have it entered and we have our plot turned on. We go to Stat, Choice 4, which is linear regression. And then we make sure our lists are L1 and L2, and then we do the vars, Y vars, to type the Y1 in there. So run a linear regression to find the equation of your best fit line after you plot it by hand. So plot it by hand first, then enter it in your calculators and find your equation. This should take, a little bit of time, so maybe we should pause for about 5 minutes here in order to give you enough time to do those two things. So about 5 minutes to work on that, and then unpause so that you can check your work. All right, so first let's check your scatter plots. So you can see mine over here in the margin. So we've got moisture content on the y-axis, frying time on the x-axis. I plotted my points in blue here, so just check to make sure that your general shape looks something like mine. For the equation of best fit, just to remind you, so you've got your data, list 1 and list 2. Then I do Stat, calc, choice 4 for linear regression. L1 and L2 store the regression equation, so vars, y vars, function, y1, and then I press calculate. So you can see that my equation, my A value is negative 0.224 approximately. So we would say our equation is y equals negative 0.224x. Then the B value is about 11.86. 860 really if we're also rounding that to 3 decimal places. So this hopefully was the equation of the line of best fit that you came up with. So number 7 then asks you to compute the predicted values and the residuals. Now this is really, really important that you follow along with me here, because when you are creating a residual graph, if you can use your graphing calculator, that will make things so much easier. So this again just demonstrates the importance of that vars, y vars step, where we pasted our regression equation here into our y equals. And if I go to my y equals screen, you can see that it's there. Negative 0.224, and then it's got all the decimal places, x plus 11 point, and then 86, and then the rest of it. The reason why this is huge is because now I can use the table in my graphing calculator to find my predicted values instead of having to plug them all in by hand. You know, it takes longer to do it by hand. Now, again, you are certainly allowed to do each of them by hand if you want. So computing the predicted y would just mean that you're taking the equation we just wrote and plugging in the x and getting the predicted y, and then we'll get the residual from there. But again, because it's much easier to use the graphing calculator, that's what I'm going to do. So on your graphing calculator, if you had this in there, if you didn't already graph it, then look at your neighbors or look at mine. But if we go to the table, so second graph, here are my y values. So I'm going to scroll because the first one I needed was for 5. So you can see them bigger over here. And what I'm going to do is kind of, let's see if I can drag this over a little bit and drag this one over also so that we can see them both. No, we can't see them both unless I am not writing, but we can look at them, you know, a couple at a time. So for 5, our predicted y value here, and we're just going to go ahead and round to 2 decimal places here. 3 makes it just a little taxing, so it'll be 10.74 for 5. Then our next value for x is 10, so that's 9.62. So we're going to write predicted y 10.74. And then the next one was 9.62. Then I go back to my calculator and I'm going to look now at 15 and 20. So I'm scrolling down. I can see the 15, but I need to see the 20. So there we go. So 15 was 8.50 if we're rounding to the hundredths place, where 20 was 7.38. So we'll record that over here. 8.50 and then 7.38. All right, next one is 25, which looks like it's 6.26. So we'll do that one. Then we're going to scroll down to get the 30. There we go, 5.13. Then 45, of course, will take a little bit more scrolling because it's further away. The other ones were 5 apart, but now we've got 15 apart. So if we keep scrolling here, there's 45. It looks like it's 1.77. So So we'll record that over here, 1.77. And then the next one we're going to need is 60. So scroll down there. And it's going too fast. There we go, 60. So negative 1.59 for that one. So just makes it a lot easier than plugging all of these values into our equation to get our predicted value. So now we want to look at our residual values. So we do y minus predicted y, so 16.3 minus 10.74, which should hopefully give us 5.56. Then 9.7 minus 9.62, those are very close together, so 0.08 is the difference here. This one, the y is smaller, so we're going to get a negative value, negative 0.40 to be exact. 4.2 minus 7.38 gives us negative 3.18. This one will also be negative 3.4 minus 6.26, so negative 2.86 there. Then 30, 2.9 minus 5.13, so negative 2.23. This one's going to be positive again, 1.9 minus 1.77, so that gives us 0.13. And then here we're subtracting a negative, so that will turn into addition, so we're really just adding these two together, which gives us 2.89. All right, next thing we want to look at is constructing a residual plot, which means you're going to plot the x's and the residuals. Oops, dragging my screen instead of circling my column. So again, take a few minutes here since it's nothing in the calculator, maybe 2 to 3 should be enough. Pause the recording to create a graph with your group of the residuals. So plot the x's, plot the residuals as your y's, and then unpause to check. All right, so check what your group came up with what I've got here. So your residual plot should look something like this. Make sure that you labeled your axes as always, but the blue dots are what your pattern should look like. Number 9 says, based on the scatter plot and the residual, would you recommend using the best fit line to describe the relationship between x and y? And it asks you to explain. So as we think here, this one shouldn't be too hard. This one is more obvious than some of the other ones. There is a very curved pattern in the residual, and even the scatter plot that we did, this does not appear to be a line. It looks very similar to exponential decay. So what I would say is a good answer for 9 is to say no, because both the scatter and residual plots show a curved pattern. All right, that is all.